talk very briefly about some of the techniques or methods to remove outliers in the data. And this is a talk intended for beginners audience, but definitely there's a lot more to cover that I won't be able to speak about. So I encourage all of you to do your research. So this is the content we're gonna see today. What are outliers? How outliers can affect analysis, data analysis, the difference between noise and outliers, and some of the visualization tools that can help us to spot outliers, statistical methods, and automatic methods as well, and some of the tips that I can give you for outlier removal. So a little bit about me. My name is Sara Iris Garcia. I was born and raised in Guatemala. I have a computer science background, and I'm currently a data analyst. I am a community leader back home. I am the leader of the Women in Data Guatemala City chapter. We still don't have a Lithuanian chapter, so I encourage if anyone here is interested in leading one, so reach out to me. I can give you more information about that. And I'm still a bit shy in the stage, so please be patient if I run out of breath when I am speaking, sorry. So yeah, what are outliers? So an outlier is an observation, basically, that lies outside of the overall pattern of our data. So there is no an agreement in the definition or formal definition of what is an outlier, but basically means that is a data different from the rest of your data. And this is a problem when we have outliers in our data. Is basically what it means is that if we are modeling based on our own data with outliers, that model can be potential biased towards a certain class based on that outlier, and basically it will skew our analysis. So we wanna make sure we don't have outliers in our data. So this is one of the examples. It's a very simple example. See, like this is a list of ages of women in a maternity guard. So you can see there, we have 22 years, 27, 30, 2 years, 32, 17, 51, and 29. I think it's quite obvious. If we are thinking about women that just gave birth to, we can see that number 2, a person of 2 years old, is potential outliers, really. And then 51 could be another outlier as well. But for this one, that is different from the number 2, because that is clearly an error in our an input error. 51, could it be an outlier for like an error, or simply is a woman who really she was 51 and gave birth? So this is how we why we need to dive into and analyze more. So yeah, so what I was saying is that these specific observations can have a disproportionate effect on our statistical analysis. So one of the first things we could do is to use our measures of central tendency. So say the mean, the median, and the mode are one of the most used measures of central tendency. And what does it mean is a central tendency means where is the location of our data, like the central point of our data. So we have these three measures. That is, it can be the first point of the starting point of our outlier analysis. If we check, if we calculate the mean, the median, and the mode, and we see if we see that these values are different, then we can see that maybe or potentially we have outliers in our data. I'm going to explain more about this. So this is an example, very basic example. We have here a table with the temperature in London for the last 7 years, 8 years. So we have for the 1st of August of each of those years, we have measured the temperature. Can you spot the outliers? I already I already put it in red. So yeah, you can see that the average, you can see 25, 22, 29, 24, 22, 26, but clearly the number 300 is, you can see evidently there is something off there. You cannot really, or can you really have 300 degrees? Really? This is an evident outlier. So let's see how this affects our analysis. So we calculate the measures, we calculate the mean, the median, and the mode. There is one column for the calculation of those measures with the outlier, and the other column is without the outliers. And as you can see clearly as well, if we see the mean with the outlier, we can see that it's that drastically changed our measure from 64 with the outlier and from 24.6 without the outlier. So we can see a massive difference. And if we see the median, can we compare with the outlier and without outlier? We can see that the difference is not that much, from 25 to 24.5. And also with the mode, we have 22 with outliers and 22 without outliers. So we can see that from this we can conclude that the median is very sensitive, extremely sensitive to outliers. And most of the techniques or algorithm will use in certain way, we will use the median. So this is why we need to focus on outliers and how to detect them. So yeah, there is, as I said, there is not like a formal definition of outliers, but also there is another definition that we have to talk about, and it's noise. So noise is usually used like this. The concept of noise is usually in the areas of frequency, like and music as well. But here we will say that noise is different from outliers, as that they are not like independent. The observations that constitute noise are not really independent. So we have different type of noise. We have a stochastic noise and deterministic noise. For the stochastic noise, is really what it means is a random measurement in our data. So say, for example, when we saw the example of the maternity, the woman in maternity guards, that number 2 was very probably a stochastic noise if we see that pattern repeating. And then we have deterministic noise as well. That is part of the data that really we cannot model. So this is hopefully you will never get deterministic noise in your data, because otherwise there is nothing you can do. But stochastic noise, we can really have can work with it. But say like an example, real world example is, say you are you want to model or forecast the weather. Say you have to forecast the weather, and if you see, like, you have your data set of the first, say, the first 6 months of the last 2 years, you have the weather. That is your data set. Then really it will appear as outlier when you have the recorder, the humidity levels when you are under El Nino storm. I don't know if you're familiar with El Nino storm, but basically El Nino is a storm that basically repeats itself every 2 to 7 years, and it is created based on certain weather conditions. So it's not something that you can really predict, but it happens. So if you only have data from, say, the last 2 years, and then the next year you have this specific change in the data, you can see, oh, this is an outlier. But if you had more points in your data, you will see that it is something that happened somehow regularly. So that will be, if you didn't see it properly, you will consider that's an outlier. But if you had more data, more information, you will see that that clearly is noise. So that is kind of the difference. That is also, this is what I was talking about graphically. There is, at the left, we have a graphic that represents the stochastic noise and the deterministic noise in the right. So you can see, like, in color blue is the actual data. And in color red is our prediction, the response. So you can model for the stochastic model, with data with stochastic noise. You can actually model that if you remove the noise from the data. You can see that clearly, that red line. You can see that that is somehow fitting the overall trend of the data. But that is, your model is able to do it if you remove that noise. But in the deterministic noise at the right, it's really hard or even impossible to model, really. And what this means, if you are working with machine learning, it will mean that your model will overfit, basically, if you have either these two types of noise. So we really also need to pay much attention of this. And about visualization tools, this is the well-known box plot. But I was talking with a person the other day. It was a user, and she was complaining that it is that box plot that we had in dashboard, it was not too easy to read, so she needed interpretation for that. So yeah, basically, it's not that easy to understand, I thought. So basically, what we are seeing here is how our data is dispersed. So in the, I don't know. Oh yeah. So here we see in blue, this is basically where the majority of our data is. So we have the minimum value, the mean, and the maximum value, but we also have these like borders here, and this border represents the IQR interval range. Sorry. So this is the interquantile range, which means it's just three deviations from the mean and 3 deviation away from the mean, like plus and less the mean. So everything that is everything that is outside this border is an outlier. So you can see the box plot is telling you that these points here are possible outliers here using the interquantile range. So if you see this in your data, you want to make sure to analyze this data here, to analyze more in depth, to really consider them as outlier or not, if really. But the box plot really is it's like an starting point. Visually, it's a starting point. So it's one of the techniques that I would use at first. We also have the QQ plot, so quantile plot. So it's as well another visualization tool to spot outliers. What we're seeing here is it's like a scatter plot, but instead of plotting two of our variables, we are plotting one variable of our actual data, and the other one is a theoretical data. Theoretical data means that you generate data based on a certain distribution. If you are very sure your distribution follows a normal distribution, then you want to generate a fake data with normal distribution, and then plot it against a variable of your data. If your plot follows a straight line, then you can say the data is normally distributed, and the points that are very far from that line, those are possible outliers. And for the statistical methods, there are a lot really to talk about, but I will give you just a couple. So three means is a very very simple method that consists basically in discarding a certain percentage of your data. So you will calculate the mean without the highest portion of the highest or lowest values of your data, and that is basically 3 means. And even if it's a simple method, it's actually very robust to outliers. So that is another useful, although very simple, but it's useful technique. We also have the Q test. This is also known as Dixon's test or R10 test, and it's basically a significance test that it is useful for when you have a very, very small data set. Because the problem is with all the methods we saw, the problem is that you really need a large number of data points. But what if you have, say, six values only in your data set? That is very difficult to use with the other techniques. So Dixon's test can be a starting point because it's very, very good for samples that are up to 40 observations. And what it is very difficult to calculate manually. So you want to make sure of using a Python. There is PyODB, PyOD, that already have inbuilt this Dixon test. But despite that it has some drawbacks, it's a very simple technique, and also you can use Grubb's test as well. It also works with a small data set, but basically these two tests will just work if your data is normally distributed only. So if your data is not normally distributed, really these methods cannot be used there. But it's good if for small data sets. And if you have a slightly bigger data set, you can also use a generalized extreme studentized deviate test. So same as Dixon test and Grubb's test, it will work only for univariate data. So that means you are only trying to assess outliers for just one variable at a time. So it's the same as basically the same as the Grubb's test and the Dixon test, but the advantage of this is that you don't need to specify the number of possible outliers that you think you have in your data. That is one of the assumptions in the other two tests, but this is overcome that limitation. And for the automatic methods, that really this is like the next level. We have clustering-based approaches. Basically, is using clustering algorithm, not for finding groups in our data, but to find outliers. Something that really, an observation or number of observations that really are very different from the rest of our data. So say algorithms such as k-means, Gaussian mixture model, KNN, all these can be used to detect outliers. So yeah, that's another techniques that you can use. And also isolation forest. That an isolation forest is basically decision trees that are used for anomaly detection, but also we can use them for outliers as well. And the way it works is, if you know how a decision tree works, is the same. It's just that you will identify the outliers in the isolation forest here as the branches that are very small. What it means is that the isolation forest was very fast to detect a single piece of data that was very different from the other. And that's why it stopped. So that is your point of your starting point to analyze, okay, this is the result of the isolation forest. So what's in these observations, then that is what you want to make sure to do it after that. And the advantage of isolation forest is that you don't need any type of labels. It's an unsupervised algorithm. So that is very useful. And so, because it's already time, I suppose. My piece of advice, I would say, is that instead of removing outliers, it's better, way better, to impute them. Impute means change the value. Yeah, so I will suggest that after careful analysis of your data set and finding there are certain observations that are possible outliers, I will, instead of just remove them, I will impute them, I don't know, based on, depending on your data set, change by the value of the rest of the mean or things like that. But it is very, you have to be very careful of removing data just because your assumptions tell you that it may be an outlier. And most of these methods that I showed are, they hold the assumption of normality. So you want to make sure of conducting a normality test before using any of these methods. Otherwise, they will give you skewed results. And also, make sure of run the model you're using with the outliers and then without the outliers. If you're using regression model, a regression, linear regression, then you can calculate that with the outliers and without the outliers and see how the R-square variance, the variance of the R-square, that's a good point of to look at. And I would say that none of this is really important if you don't know the data you're working, because it's not the same as saying like working with weather data, working with healthcare data. Like really, the subject matter expertise is vital here. And just because one of the outlier detection methods indicates that you have probably presence of outlier doesn't mean that you can straight go and delete them in your data. So always, if possible, have the support of a subject matter expert, and yeah, be safe and conduct many tests, because you really don't want to make more, bring more bias in your data with your analysis. So that will be how to remove outliers in your data. And yeah, if you have any questions or want to say hi, I don't use social media anymore, but you can find me in LinkedIn still. So thank you.